Hi class, welcome to your lecture that starts chapter 6. Chapter 6 is going to be about what we call quadrilaterals. So we'll jump right into section 6.1. Section 6.1 is going to talk about what in mathematics what we call our polygons. So we have two objectives in this section. First, we want to name and define different types of polygons. And then the last thing we're going to do is we're going to find the sum of the measures of the interior angles of a quadrilateral. And that'll really be, the first part here is going to be a lot of definitions and identifying things. And this will be the first time we jump in and do some arithmetic or algebra. All right, so some definitions. So a figure is a polygon if it meets the following conditions. Like, what is a polygon? Well, first off, it's a plane figure formed by three or more line segments called sides. The sides here, right, sides that have a common endpoint are non-collinear. What that means is that the sides don't follow a straight line. And each side intersects exactly two other sides, right? But only at their endpoints. So the endpoints of the sides of a polygon are what we call the vertices, right? Or singular of that is the vertex. So like here are the vertices, right? The endpoints of the sides. Okay, so below are some examples of polygon. Each vertex of the middle polygon is labeled, so a polygon can be named by listing its vertices consecutively in order as shown. So here a triangle is a polygon, right? Like each of their sides intersects only two, or each of the endpoints intersects only two lines right here. Same with this, right? Or a star, that's a polygon. It has straight lines that each point only has two lines that go to it. So you can name a polygon by, I said, as its vertices. So polygon D, E, F, G, H, right? Those are the sides or the vertices in order. It can also be polygon E, D, H, G, F. It doesn't matter as long as you say it in order like that. All right, so identifying a polygon. So identify the polygons. If it's not a polygon, let's state why. So as you look through these, right, this one I don't think is a polygon by our definition. This one not. I'm not sure about this one, but by definition, this might be a polygon, and I think this might. All right, so figures A and E are the polygons here. All right, they meet the definition. They have these straight sides. Okay, each endpoint only has two sides that go to it. So even though this one looks like a wacky shape, all right, it's still a polygon because it has these straight sides that are all connected. All right, figure B is not a polygon because there's a side that is a curve that is not a line segment. So any curve like this would mean it's not a polygon. All right, so that leaves C and D left to talk about. Figure C is not a polygon because by our definition, there's a side that intersects more than two other sides. So like if you think about it, like right here, this point here, it has 1, 2, 3 sides that intersect at that point. That means it cannot be a polygon. Same thing over here, 1, 2, 3 sides. And part D is not a polygon because two sides intersect only one other side. So like this side here intersects only this side, and this side here intersects only this side, right? So like this one here, this side intersects, more than two lines. Wherever you have like a point that has three lines into it, something's up. Or if it doesn't connect, right, that means it's not a polygon. All right, so we have very specific names based on the number of sides polygons have. So if it's 3 sides, it's a triangle, 4 sides, quadrilateral, 5 sides, a pentagon, 6 sides is a hexagon, 7 sides is a heptagon. If it's an 8-sided shape, it's an octagon. 9-sided is nonagon. 10-sided is a decagon, and a 12-sided is a dodecagon. After that, I mean that's enough right there, and you don't have to memorize these. But if anything that has n sides, we just call as an n-gon. So in general, a polygon with n sides is called an n-gon. For example, a polygon with 13 sides is just called a 13-gon. All right. Another way to classify polygons is as convex or concave. So a polygon is convex if no line containing a side contains a point within the interior of the polygon. And a polygon is concave or non-convex if it is not convex. So it has no points that are inside the interior of the polygon. All right, so what do we mean by that? Like convex, there's a point within the interior. Concave, no points in the interior. All right, let me show you. All right, so identify the polygons. If it's not a polygon, state why. So this one right here, This one, A, is a polygon. Its eighth side, so it's an octagon. Notice none of the extended sides contain a point on the interior, so there's no side that like bunches into it. So this is convex. B, this is a polygon that has 6 sides. 1, 2, 3, 4, 5, 6. So it's a hexagon. All right, some of the extended sides contain a point in the interior. Like notice how this side comes in like this. And so the point seems to like branch inside. This means it's concave, where this one was convex. This one over here, this is also a polygon that just 4 sides, so it's quadrilateral. None of the extended sides contain a point in the interior, so it's convex. So concave if it comes in, convex if it doesn't. All right, an equilateral polygon is a polygon with all sides that are congruent. It's like this. Notice how each side has the same length. An equal angular polygon is a polygon where all the angles are congruent, like this. All the interior angles are the same measure. An irregular polygon is a polygon that is both equilateral and equal angular. So something like this. All the sides are equal and all the angles are equal. All right, so determine if each polygon is regular or not and explain. So this one right here. Remember, to be a regular polygon, you must have all the angles the same, which it looks like, and all the sides the same, which it looks like. So A, the pentagon here, is an equilateral and equal angular, so it's a regular polygon. If you look at B, all the sides are the same, so it's definitely equilateral, but it doesn't look like the angles are equal. So for B, this hexagon is equilateral, as I said, but not equal angular, right? So it is not a regular polygon. When you go to C here, it looks like the sides are all the same, but opposite angles are congruent, but not all 4. So this quadrilateral is equilateral, but not equal angular, so it is not a regular polygon. All right, a few other definitions. A segment joining 2 non-consecutive vertices of a convex polygon is called the diagonal of the polygon. So like this one and this one, they're non-consecutive, right? Because like consecutive vertices would be here and here, but like this. So a quadrilateral has 4 sides. Note one diagonal forms 2 triangles here. A pentagon has 5 sides, so 2 diagonals form 3 triangles. And a hexagon, 6 sides, when we do these diagonals here, form 3 diagonals, which form 1, 2, 3, 4 triangles. All right, so remember that diagonal, non-consecutive vertices. All right, one theorem. This is the interior angle sum of a convex quadrilateral. So the sum of the measures of the interior angles of a convex, remember that means it doesn't bunch inside, quadrilateral, is 360 degrees. So if you were to take measure of angle 1, measure of angle 2, measure of angle 3, measure of angle 4, if you add them all up, you get 360 degrees. All right, so this one right here. Let's find x and then the measures of the angles C and D. C and D here that we don't know. Well, this polygon has 4 sides. Right, 1, 2, 3, 4. So it's a quadrilateral, which means if I sum all their interior angles, they must sum 360 degrees. So combining like terms here like this, right? You get x plus 2x gives me 3x. You sum all these numbers here, you get 255. Subtract the 255 over, divide by 3. You get x is equal to 35. So we can use x is equal to 35, find the measures of angles C and D. Well, the measure of angle D is the easiest. That's just 35 degrees. Next, to find the measure of angle C, just plug it into here. You get 2x plus 3, or 2 times 35. Pardon the typo here, right? There's an extra 2 there, but 2 times 35 is 70, plus 3, which is 73 degrees.